Hello everyone, welcome back, or hello if you're just joining now. This is the next milestone in my Tic Tac Toe electronic project. Sort of started this Tic Tac Toe project up as a way to learn about electronics and how everything works. I know how to code pretty well, but I never really understood all the makings of electronics. And let me just get a good zoom in, a panoramic view of all the circuitry that's happening right here. It's pretty daunting with all those red wires crossing each other and this massive heap of just chaos coming out of the ThinkPad. Right, well, not ThinkPad, Launchpad. This is a Texas Instruments products. Well, actually, this is from Mauser, random manufacturers. So yeah, this is the first tic-tac-toe project, and my actually first project that I just sort of did on my own and made 100 mistakes along the way, so it was pretty fun. But now we got it working, and LEDs are working, buttons are working. Started back in January, maybe early, I'd say January 7th, I started getting pieces for this to sort of put together, and knew that I wanted to create a tic-tac-toe project as a first stepping stone to more larger and ambitious electronic projects. So it was a great experience. Not done yet. I still want to do a couple other things, a couple experiments and such before I move on to other things. My intermediate milestone was on February 11th, which just featured LEDs and a extra breadboard over here for transistors. That went away with the purchase of a LED driver, constant sync LED driver, that is. So without further ado, let's kick this bad boy up and play some tic-tac-toe. It's been 3 months in the making. Might as well see how it works. Those are O's, X's, O. So just a little startup feature saying X's turn. So it's and I didn't put the buttons right where the LEDs are because it was just too crowded. It was just, you can't do that. It's just, you need some space. So O goes the middle. Terrible move on X's part. But you know what? O is not too bright. He's going to lose this one. So let's do O right here. I keep going for the LEDs, holding the camera at the same time. X's turn. Let's complete the column. And it shines bright. LEDs showing the row is lit up. Going out of focus. And restarts the game. Starting over, saying, hey, there's a tic-tac-toe game. X goes first. And then let's just go ahead and see what happens when there's a tie, just to show you guys what happens when a tie occurs. Hopefully, one time I actually messed up and didn't know how to get a tie. I was sort of guessing spots to pick, and then it ended up like X would win either spot. So stupid me. I'm not paying attention again, so if I totally mess up, sorry. Is that, oops, let's put O right there. X's turn. X blocks him. And O, oof. And it's a tie. And the LEDs go away one by one. And then we start over again. Okay, cool. Cool. So that's the game. And, right now it's all on breadboards and with wires going all over the place. It's not usually how it's done. There's usually a copper board, and then you etch out the copper to be your wires to go to these integrated circuits and your components and such, and also go to your battery and whatnot. Yeah, let's go over it, and that's the game. Let's go into more of the technical savvy stuff. So if you want to listen on, I'm just going to explain how everything's working. If you're not interested, thanks for watching. And I'll post you a next video with hopefully everything on a copper board and it operating on its own batteries rather than the laptop energy. So, be completely independent. Okay? So let's go right into the technical guru stuff. I'm not going to go into code. I'm just going to go into wires and what parts are what and what happened since February 11th. February 11th, we had some transistors over here on a breadboard. They are gone. They used to be controlling some of the LEDs on that LED rows, which LED rows are going to be lit up with these transistors over here, but now they're gone, and in replace of that is an LED driver, constant sync. Why did I do that? That was because of a problem. It was because of a problem. This constant sync LED driver, it'll sync current evenly across all LEDs. With transistors, the more LEDs you have on, or the way I had it wired, the more LEDs you had wired on, the fewer the current, less current will be distributed over the LEDs. So the light intensity would actually decrease. With this constant sync driver, it does the work for me, and all LEDs get the same intensity all the time, which is really cool. And I get to choose what the intensity is by this resistor right here, which is connected to the ground. And that value will actually determine what's what in this LEDs. And I chose it around to be 30 milliamps per LED. So most LEDs operate between 20 and 40, and then go up to a maximum of 50 before it becomes super hot and blows up. So you don't want that. So I just kept it, a very conservative value. Let's see. Oh, and the counter register. So let's go over, just some of the things I mentioned in the February video. This is a shift counter. It's basically tells which columns should be on. And these LEDs are in parallel in columns, and they're also in parallel in rows. So these guys control which LEDs are on. And how is this guy controlled? Is controlled by the microcontroller with all these jumbly wires coming out. We see that there are a few wires attached to this shift register, which these two wires are attached to those two bottom pins, and that red wire is attached to the top pin, and you see a little metal piece right there making those two top pins interconnected. They both have to be the same value in order for it to register a value. And those inputs will control those green wires going over to the columns. And then we got our LED driver on that side, the top black IC, with those three red wires, and they're going to the rows. Essentially, those red wires right there are outputs. So we get to enable which one is actually completes a full circuit through this IC and heads to the ground right here. So, with that, we got one controlling the rows, one controlling the columns. We could easily do a X and Y, which ones are turned on using X and Y components, X and Y grid. So that's how that works. With fewer wires, you could easily do that. Instead of actually completing a circuit with each LED, you just go ahead and say, hey, I'll control columns and rows, and then boom, that's how you got each LED on and up. So that's pretty cool. That's how you do that. And I always find that fascinating. Hopefully the audio doesn't get distorted. I'm making sure not to press my finger on top of the holes for the audio in the camera. And I'm trying to hold this as steady as I can, but I need a tripod eventually for holding this camera, or just like a book. A book would do nicely. So in any case, here's another shift register in the middle, and it connects to these very long red blue lines going across. And it basically does the same thing, except a very much more basic thing than the LEDs. The LEDs need to be a little more complicated. The buttons, I sort of just say, hey, connect the rows. All the ones are in parallel in columns, all in parallel in rows. The only difference is I just use it doesn't need to be the same current. All I have to do is just apply a current to the buttons. And the buttons will, once they're pushed down, will complete a circuit going up here, connecting these green wires over here. Let's zoom in over here. Connect to a resistor, and then connect to these input wires, which go back to the microcontroller. And what these guys are, you might not know where these guys are connected to, but these guys are connected to metal pins, which go onto the circuit board and then into this, into the pins of this microchip. And a little thing about this microchip, it only has 256 bytes of RAM and 16 kilobytes of program memory space. So there's no operating system or anything on that. So you're on your own when you're coding. It's you and the processor. There's nothing else in between. And this Tic Tac Toe project took about 2.7 kilobytes of memory space to control the whole thing. I'm sure you could have, if I cared enough, if I wanted to do it better, I probably could get it down to a kilobyte. And it took up half the memory, 120 bytes of RAM usage, to actually memorize the state, and then also, any variables that need to be done. So, that's how it generally works. I just basically glossed over everything. I'm not going to go in the code, but the code basically says, hey, control these guys, change up which wires or what values, and be able to control the LEDs using these components, these output wires. Yeah, so I mean, I'm not going to go into too much detail, but that's how it works. And now the next step I sort of want to do. Oh, well, actually, another challenge I faced. Most recent one actually was the double tap on buttons. These buttons, you can only push one button at a time. If you push two, the microcontroller freaks out. That's because they don't have any diodes. LEDs have a diode implicitly built in with them. They need that. Diodes for buttons, they don't care. It's just a wire in between. It completes a circuit when the button is pushed down. So the current could go either way. But eventually, if you want to push down multiple buttons at the same time, you need diodes. Another thing I bumped in with the buttons is that a double tap. When you push a button down, you're not a machine. You could accidentally make a mistake, and your joltiness will double tap it very quickly, and the microcontroller actually doesn't have time to process both button taps within the allotted time. Now that could be because of my code, but I was stuck in a situation where I had to run a little bit of a longer interrupt code to process if that button push was correct, where that button was pushed, etc., etc. So I needed to do some magic, coding magic, to basically say ignore all future button pushes after this one, and then re-enable button pushes in a quarter of a second later. So that was the one way I dealt with that stuff. But when I get into more complicated stuff that needs multiple buttons, such let's say if I'm making a keyboard, you're gonna need diodes, which is gonna increase the cost, of the project, and then also I'm gonna need to reconfigure the code a little bit better to handle the button pushes faster. Otherwise, the keystrokes are just gonna overwhelm this microcontroller, and it's just not gonna register. Another thing is this microcontroller only runs at 16 megahertz. So it's very, very basic, very slow. I'm sure even 10 years ago or 15 years ago there's faster processors, but this is literally the cheapest microcontroller you could get. It's only $2. And for what it's worth, it does its job. It consumes little to no power, and I'm on the fastest speed right now, and you could actually configure it to barely run at all. And it could just stay on forever, which is cool. So yeah, the next part, let me just see if there's anything. I just built a checklist to go over some things. But next part I want to go on is take this guy off this board and put this guy right here and attach a voltage regulator which says how much voltage the chip will get, and attach some batteries to that voltage regulator, and then get it to run by itself rather than being connected to the laptop. And then once I have that down, I'm going to put this all on my copper board and get rid of all these wires and just have the wires built into the copper board itself. That's what essentially copper boards are for. It's just wires built into a board rather than have this tangled mess that's much more expensive. And that's a permanent solution, so I hope I don't mess up, and it requires some soldering skill. But I'm up to the task since, well, it's the next step in learning. So another thing I like to do is get an external flash memory. For like 50 cents, you could buy 8 megabytes, and it looks just like a chip. And connect and store some audio on that, and see if I could get a speaker system to play some sounds. But that won't be in this project. That'll be sort of an independent project I'll do just as a little experiment, see how that works out. But for the most part, this is wrapping up. There's not going to be any new functionality to this Tic Tac Toe besides putting a battery on it and seeing if I could get everything to work together. So yeah, that's how everything is rolling. Let me know if you want to see anything, or if I just missed over something completely, or any corrections, because I'm still learning. There's only been like 3 months of learning so far, and it's been pretty fun. So hopefully the next projects get a little bit more ambitious, more exciting. Things happen. So yeah, okay. Well, thanks for watching. Maybe in a month or so, I'll have my next milestone out for this Tic Tac Toe project, and you guys see a full what a voltage regulator looks like, or even that, maybe an AC adapter. Who knows? That might be even tougher. I don't know. I don't know if I want to do that. All right. Well, anyway, thanks for watching. Tune next time. Tune next time, folks.